Section 7.3 is about solving equations using quadratic techniques. Sometimes we have expressions that are not in a nice form for us to use. And one of the strategies we can use is we can rewrite those forms into quadratics, thereby turning a problem that we can't do into one that we can do using a quadratic form. So instead of using the letter x and having ax squared plus bx plus c, we use a u. And that u can be anything, any expression, any combination of numbers and letters, as long as it's something squared, and then in the middle term, something to the first power. So let's try to rewrite some of these examples in a quadratic form, starting with the first one. If you look at the middle term, it's x squared, and I want it to be something to the first power. And in the beginning term, it's x to the fourth, and I want it to be something squared, so I can write it as a quadratic. So I'm going to say that my u equals x squared. So what I'm going to do then is instead of x squared, I'm going to put a u in. So now if I square x squared, or square u, I get x to the fourth. Then I'm going to say plus 13u, because remember u is x squared, and plus 36. So now this looks like a quadratic, something that we've seen before with a square and a single u and a number on the back. And so we could solve this using quadratic techniques. Now what is this really? Well, since u is x squared, I'm going to rewrite it as x squared squared plus 13 times x squared plus 36. So that's really what we're doing, is we're replacing the x squareds with u's, and then we're actually going to solve this one on the next slide. We'll see that in a minute. In this one over here, I'd like something squared. So what can I square that will give me a 16x to the sixth? Well, if I take a 4x cubed and square that, it'll give me a 16x to the sixth. So I'm going to say u squared minus 625. Because 625, the square root of that is 25. So 625 is really just 25 squared. So that's okay. This creates a difference of squares. If I rewrite it another way, 4x cubed minus 625, 4x cubed squared. And so that's what it would look like, either by using a u to substitute or by actually putting the 4x cubed in there. Next example, we have an x squared in the middle, so it looks like I should take u and substitute an x squared. The problem with that is that's not going to help me over here, because x to the eighth doesn't come from an x squared squared. That won't work. That'll give me an x to the fourth. And there is no number that I can square to get a 12. So this example is not possible. There's no way I can rewrite this in a quadratic form. Over here, we have an x to the 1/2 in the middle, so I'm going to make my u x to the 1/2. It turns out that if I square x to the 1/2, I'm just going to get an x, and this will be a 9u plus 8. So rewriting this, this is actually going to be x to the 1/2 squared minus 9 times x to the 1/2 plus 8. And let's see if you can understand that. X to the 1/2 squared, it gives me an x to the first power. So I'm able to rewrite it as something with a square on it, and then have that same base with a first power in the middle, and now it's in quadratic form. Here are some examples that I'm going to solve by putting them in a quadratic form. This is the first example that we did. We said we could make this an x squared squared minus 13x squared plus 36. And so now it's in quadratic form. It has a square in the front, something to the first power. I mean, this is technically x squared to the first power plus 36. Now, if this was just a trinomial, we'd use the diamond and we'd say, what two factors of 36 add to be negative 9? And those two factors are going to be negative 9 and negative 4. Now, what goes in front? What goes in front is the base of the squared term. So I'm going to put an x squared here and an x squared here, because x squared times x squared would give me x to the fourth. And now we go ahead and solve. Now before we can solve this, we notice, hopefully, that these are both difference of squares, which will factor again into x plus 3, x minus 3, and x plus 2, x minus 2. And then using the zero product property, we find that there are four solutions here. negative 3, positive 3, negative 2, and positive 2. In this example, we see an x cubed with an addition sign, which hopefully should make you think of the sum of cubes formula. And so we want to check and see if 343 is a perfect cube. It turns out that it is. It comes from a 7 cubed. So we're going to use the sum of cubes formula using x and 7 as my two values. So that pattern makes us put an x plus 7 in front, and then a trinomial inside with a square of the first term, the opposite sign of what's in the middle up here with the terms being multiplied, and then the square of the last term on the end, which is a 49. Now we'll use the zero product property, set each group equal to 0. This one's a little more complicated than the last one, so I'm actually going to write it out. Over here, we'll subtract the 7, and so one of our solutions are going to be x equals negative 7. But this is a little harder. It's a trinomial that it can't be factored. I can't find two factors of 49 that add to give me a 7. So I'm going to have to use the quadratic formula. And remember, I'm going to say my a here is 1, my b is negative 7, and my c is 49. So let's plug that into the quadratic formula. So the opposite of our b, plus or minus our b squared minus 4 times a, which is 1, times c, which is 49, all over 2 times 1. Simplifying, we get a positive 7, plus or minus, this is going to be 49, this is going to be minus 196 over 2. Simplifying some more, 7 plus or minus negative 147 over 2. Because we have a negative underneath the radical, hopefully you know that that means we're going to have some imaginary numbers. So I'm going to take that negative sign out by making it an I, because remember that's a negative 1, times the square root of 147 over 2. So these would be my other two solutions, because there's a 7 plus and a 7 minus. So I have solutions that I found up here, negative 7, and I have solutions that I found down here. So really there are three solutions to this problem, which we knew because the highest degree on the polynomial was a cubed, so we knew we were going to have three solutions. Here's another example, this time with fractional exponents. I'd like to put it in quadratic form. I noticed that x to the 1/3 can be used as my basis, so I'm going to make that x to the 1/3 to the first power, and then I also noticed that this could be x to the 1/3 squared, because 2 times 1/3 is 2/3, and so now it's in the quadratic form. Using a diamond, I'm looking for two factors of 5 that had to be negative 6. That's going to be negative 5 and negative 1. Now what goes in the front? The x to the 1/3 does. So now I'm going to use the zero product property on each one of those. Set each one equal to 0, and then I'm going to solve. Here we'll add 5 to both sides, so x to the 1/3 power equals 5. How do we get rid of a 1/3 power? We take it to the third power, because x to the 1/3 cubed is actually just an x. And then 5 cubed is 125, so that's one of my solutions. Similarly over here, x to the 1/3 power equals 1. Getting rid of a 1/3 power by multiplying, or by cubing it I should say, gives me an x equals 1. Because fractional exponents are actually radicals, I've got to plug these two back into the original to make sure that they both really do work. So plugging them back into the original, remember that the 1/3 power is really the cubed root of 125, and then the square just means to square that. Well, the cube root of 125 is 5, and 5 squared is 25. Minus 6 times 125 to the 1/3 power is a 5. And let's see what this is. So 25 minus 30 plus 5 does equal 0. So that's one of my solution that checks out. That works. Now I'm going to plug the 1 in and do the same thing. Well, 1 to any power is just 1. So 1 minus 6 plus 5, that easily equals 0 also. So I'm going to write my two solutions this way. 1 and 125. Here's our last one. I'm going to rewrite this as x minus 6 root x minus 7. Want to get it equal to 0. And now if this was in quadratic form, things would be a lot easier. So I'm gonna take this square root and kind of use it as my base. If I write this as the square root of x squared, that will give me the x that I'm looking for. But then I can write the middle term just the way it is, 6 times the square root of x minus 7. And so now I'm left with a squared term, a single to the first degree term, and a constant. So now I can use all my quadratic form shortcuts. I need two factors of -7 that add to be a -6. I can't think of any that work that way, so I'm going to have to use the quadratic formula. Now typically when we have the quadratic formula, we say x equals. But we only say that when x is kind of our foundation value here in the middle. In this example, it's not x, it's the square root of x. So we're going to say the square root of x equals all that and plug into that formula. My a equals 1, my b equals -6, and my c is -7. So let's plug those into the quadratic formula and solve. So the opposite of negative b, or the opposite of b, plus or minus b squared minus 4 times a, which is 1, c, which is -7, all over 2a. Simplifying now, we got a positive 6. This will be a 36. 7 times 4 is 28. With two negatives makes it a plus 28. And all of that's going to be over 2. This works out nicely because the square root of 64 is just going to simplify to be an 8. So there are really two solutions. There's a 6 plus 8 and a 6 minus 8. So I'm going to write them both over here. 6 plus 8 is 14, and 14 divided by 2 is 7. And then 6 minus 8 is -2, and -2 over 2 is -1. So my two solutions, 7 and -1, but they equal the square root of x. To make them equal x, I'm going to have to square both sides. So x equals 49. Now this one over here, I'm not even going to bother squaring because we know that a square root cannot equal a negative. So this one obviously cannot work, which means x equals 49 must be the only solution.